We have one more problem here for 7-1. This is a pretty typical kind of problem to see on the AP test. Watch how many different things that we've talked about this year come together in a problem like this. So we have a beach. There's a certain amount of known amount of sand on the beach at a certain time. And then two things happen. The tide is taking sand away, and then they've brought some sort of machine onto the beach to put sand back. It's pumping sand back onto the beach at a rate that we know. So we're gonna just practice noticing which of those rates are important to us at which times, and we'll see how we do here. So question A says, how much sand will the tide remove from the beach during this 6-hour period? Notice this question has nothing to do with how much sand was there at the beginning. It has nothing to do with how much sand is, oh, that's why we can't see. That's what's missing. Okay. I was missing the rest of my problem. So it has nothing to do with how much sand was there at the beginning. It has nothing to do with how much sand is getting pumped in. Those things aren't going to help us answer question A. Question A is just about how much sand gets taken off the beach by the tide, and we have the rate at which that happens. So I'm going to integrate that rate. I'm going to integrate from 0 to 6. You could write this whole function name in, but you have no obligation to. Simply write r of t dt. That's worth 1 point for writing a correct integral expression, a second point for typing it into your calculator correctly and giving units. My calculator tells me that that is 815.815. What are the units going to be? R and S have units of cubic R yards per hour. So R is measured in cubic yards cubed per hour. And I'm multiplying by time, which in this case 0 and 6 are both measured in hours. So the hours cancel, and my units here are yards cubed. Or I could have written out cubic yards. That's my answer to letter A. Letter B, sometimes they don't ask you to write this equation, but I'm going to recommend that you practice writing this equation because it's going to be, even if they don't ask for it in other problems, it's going to be your key to answering here. So, an expression for y of t. Well, here's the thing. Y of t. The amount of sand on the beach depends on 3 different things here. We've done similar problems that only depended on 2 things, a known value, like an initial value, a starting value, and a derivative. Here we have 2 derivatives. We have 2 rates. One is a rate coming in, and one is a rate of sand going out. So I'm going to have 3 pieces in my function. It's going to be the starting value. So the amount of sand on the beach at time t depends on the amount of sand we started with, which was 2,500 cubic yards, plus the amount of sand that comes in over that time, the time being t, so from time 0 to t, and the amount of sand coming in is s of t, except I can't use t because I'm using it as my upper limit. Pick another letter. And I have a rate at which sand is going out, so I'm going to subtract out just this exact same integral that I wrote there, except I cannot use t. This is going to be 0 to t r of p dp. So the amount of sand on the beach depends on, that's my final answer, I'm just going to sort of highlight here. The amount of sand I started with, plus the amount of sand that comes onto the beach from time 0 to t, minus the amount of sand that goes away from the beach from time 0 to time t. So this is my expression. Letter C is a derivative question, so it's good to remember that we still understand about derivatives. Find the rate at which the total amount of sand on the beach is changing at time t equals 4. This question you could answer without having answered letter B, but since we've answered letter B, watch how fast this goes. I'm going to move me out of the way. So find the rate at which the total amount of sand on the beach is changing. Well, the rate of change of the amount of sand is going to be y prime because y was the amount of sand. So what I want is y prime. What I want is y prime of 4, but don't tell me an expression, don't tell me y prime of 4 until you can write me y prime of t. Y prime of t, well look, there's my function. The derivative of 2500 is 0. The derivative with respect to t of the integral from 0 to t of s is s with the input variable changed to t minus. So that was a very easy derivative to take as long as I remember the fundamental theorem of calculus and how to take the derivative of a function defined with an integral. So now, I'm not doing part D, I'm finishing part C. Y prime of 4, 4 is going to equal S of 4. Wow, keep writing T's. S of 4 minus R of 4, which my calculator tells me is negative 1.908, and that's cubic yards, yards cubed. So notice here, S and R both have units of cubic yards per hour. So cubic yards per hour. Because S and R have the same units, so when I subtract values that come out of S and R, the result still has those same units. So negative 1.908 cubic yards. A question they did not ask us, but I'm just going to kind of front load it here because they will definitely ask you somewhere on the AP test. The question here, given that this was the rate of change of the amount of sand on the beach, is the amount of sand on the beach increasing or decreasing? Well, I hope you can tell that because the derivative of the amount of sand is negative, the actual amount of sand is decreasing. That means the tide at that point at time 4, the tide was taking sand away faster than the pumping station was putting it in. All right, let's look at letter D. All right, this last question is great because we have to bring back everything we remember about finding absolute extrema, and now we can use integrals to help us. So if I want to know at what time t is the amount of sand on the beach at a minimum, that means I want to minimize, I'm going to write it up here, minimize the amount of sand on the beach. And I've actually already written a function that tells me the amount of sand on the beach. I called it y of t. And just to be clear, I only care about the time interval 0 to 6. So I have to remember the steps for an optimization problem. I figured out that I want to minimize y of t. I already have a y of t function. You'll notice that since when we wrote it before, I wrote 2 separate integrals. The integral of s minus the integral of r. Just remember that you can add and subtract integrals. So I've written this, it just takes up a little less room. The integral from 0 to t of s minus r. So what do I need? I'm going to need the derivative of y, but that's okay. We already figured out y prime is, s of t minus r of t. And what do I need to do? I'm going to make a table of values. And I need to know my candidates. I want to maximize the amount of sand, which I called y. My candidates are times 0 and 6 because they are the endpoints. And any critical points of y. Well, critical points of y are places where y prime equals 0. So I'm going to use my calculator to solve this equation, y prime equals 0. Here we go. All right, so I'm going to let y prime equals 0. So y prime is s of t minus r of t. There's a couple ways to do this. You could type y equals 0 into your calculator and y equals this subtraction problem and look for, essentially you're looking for places where this function crosses or touches the t-axis. Another way to think about it, you can imagine adding r of t to both sides. You're looking for times where the incoming sand, the sand is coming in at the same rate as sand is going out. So that's probably what I would type on my calculator. I'm going to type those two functions and set them equal to each other. And my calculator tells me that that happens at time t equals 5.117 seconds. Not seconds, hours. 5.117 hours. There we go. All right, so now what do I need to do? Well, I need to figure out y at those three time values, and I'm going to pick the y value that's the smallest. I'm going to figure out the time that happens, and I'm going to report, because they've asked about what time, and they've asked about the actual minimum value. So I know at time t, this one's easy. I don't even need my calculator for this. I've been told at time t equals 0, there are 2,500 cubic yards on the beach. What I'm going to do next, I'm going to go back to my y function. I'm going to replace t with 5.117. My calculator tells me that that is 3694 cubic yards. And at time t equals 6, if I replace all the t's in my y function with 6, I get 2493.2766. All right, now I have enough information to write up my answer. All right, so here's what you have to do to get full credit for an optimization problem on the AP test. You are going to have to give a justification for why you only had to check those three values. Because it's not clear, like maybe why do we only have to check those three values? So the reason is a calculus reason. It's calculus knowledge that you have, which is that an absolute extreme value is going to occur at an endpoint or at a critical point, which is the possible location for a relative minimum or relative maximum. So that's the key part in your write-up. I'm going to type it up. All right, this is the first half of my answer. I'm giving my reason why I only had to check time 0, time 6, and time 5.117. I say the candidates for the location of the absolute minimum value of y of t are times 0 and 6, the endpoints, and any solutions of r of t equals s of t. This part, you could have written anything that's equivalent. So we could have said y prime of t equals 0, or 0 equals s of t minus r of t. Just notice that works because we had already defined the meaning of capital Y of t. In other cases where they don't ask us to write that function, you're going to have to be specific. You might have to say the candidates for the location, or you would say the candidates for the time of the absolute minimum amount of sand on the beach, and you'd want to be very specific that you are referring to the quantity that they asked for. All right, the second part is actually just reading from your table and figuring out what that smallest value is. All right, so then you can read the answer from your table. This is the smallest of the y values in my table. And I would say the absolute minimum amount, that should have an n, amount of sand on the beach occurs at time t equals 5.117. At this time, there are 2,492.369 cubic yards of sand on the beach. So common errors, which I hope you will avoid. This word here could have been time because the input to the y function is time. What you really don't want to say, the error would be to say that the candidates for the absolute minimum value of y. Because the minimum value of y is a y value. What we're trying to justify is our reason for only checking those three inputs. So you have to be careful that you're referring to whatever the quantity for the input is. If you don't feel like you've really understood that, then make sure you're saying the location instead of saying the absolute minimum. Okay, so like I say, there's a problem like this almost every year in the free response section where you have it like an in rate and an out rate, and you need to make decisions about when the minimum or maximum occur, whether at any point the amount of something is increasing or decreasing. So check for one of these pretty much every year in your free response book, and they're really good practice to make sure you remember all kinds of topics from the whole school year.